Pore engineering is all about designing and controlling the teeny holes or pores inside a material. We control their size, shape, distribution, and how they connect with each other. This is also very important. Now, because of force directly affect properties like sound absorption, strength, and how the material interact with air and liquids. In this presentation, we will focus on how pore engineering in slag-based material can improve sound damping. Now coming to our next slide, which is about why manage pores in slag for acoustic application. Slag is a byproduct of a steel and iron production, and it can be reused to make acoustic material. The reason we focus on its pores is simple. Sound waves interact with these pores first. When we optimize pore structure, sound waves lose more energy inside the material, improving noise absorption. This makes slag not just a waste material but a valuable, sustainable resource for noise control. Now, key pore characteristics in acoustic materials. If we consider, then four main pore characteristics affect acoustic performance. First, pore size. The best size range for absorbing sound is about 25 to 100 micrometers. The second, pore distribution. We want a uniform size spread plus a mix of a small and large pore for different frequencies. Third, the pore connectivity. Interconnected pores make sound travel longer paths, losing more energy. And finally, total porosity, which is the percentage of the material that empty space. So we come across the information that the main thing, the main success is behind the pore engineering. If we engineer the pore structure, the pore architecture, the pore distribution, the pore sizes well, then we have succeed in obtaining maximum sound absorption capacity of these pores. Now coming to this slide, which is about how pores influences sound damping mechanism. When sound waves enter the pore, they scatter and lose energy because of friction and teeny air movement inside. Very small pore tend to reflect sound, while very large pore let sound pass without much loss. That's why an optimal medium pore size work best. Interconnected pores force the sound to travel longer, more complex paths, which increase energy loss and improves the damping capability. Now, in this slide, we are going to talk about how pore size distribution can be controlled. We can control pore size with different methods: physical foaming, such as gas injection or adjusting mixture pressure, control the initial bubble size; chemical foaming using blowing agent or chemical reaction regulates how much gas is released and how fast; changing the binder or polymer content adjusts viscosity, which affects how bubble grow or merge. Temperature and pressure during foaming also influence how big and how uniform the pore size. Now, in this simple process parameter, effects on pore has been shown. In simple term, higher polymer concentration gives smaller and more uniform pores because the mixture is thicker. Increasing foaming pressure makes larger and less uniform pores. Higher temperature reduces viscosity and allows larger pore to form, but too high can cause pore merging. Fast solidification freezes the pore structure in place quickly, gives better pore size control. Now, where does this pore engineering fit in material design? Pore engineering happens during material production, mainly during mixing, foaming, and curing. This is when we can control foaming condition additives, and setting time. Even after production, post-processing treatments can adjust pore connectivity or surface texture. In practical use, pore engineered slag is applied in things like acoustic panels, permeable asphalt, and lightweight foamed concretes. So why start with the pore engineering? We start with the pore engineering because pores are the first microstructural feature that interact with incoming sound. If we control them well from the start, we ensure the final product has the right acoustic performance. It also let us design the material for specific noise frequencies while keeping structural strength and sustainability in mind. Simple takeaways, we can say that to summarize, pore engineering means designing the size, distribution, and connection between pores. The best pore size sound damping is about 25 to 100 micrometers. We can control pore characteristic using foaming methods, process setting, and material composition. With well-designed pores, slag becomes an effective, eco-friendly material for sound absorption.